It hasn't happened yet because I think they're on lunch break, but I have a whole load of people on the roof banging and thumping things because we're getting a new roof. And as far as I can tell, it's going to take them a few days to do it. So just warning you, if you think there's an earthquake, there's not. It's just the guys making a mess. Of course, my dogs don't like it, so you'll also get some barking and all sorts of other fun things when that does eventually happen again, because they've been doing it all this morning. So we're going to look at Jacobians. It's part of section 15.9, which is last party 15, I believe, and it's change of variable. It's equivalent to 2- and 3-dimensional versions of U-subs. And so we're going to look at, as I said, how to find a Jacobian. That's what a Jacobian looks like, at least a 2x2 does. And then how you can translate a Jacobian using it to find a double integral that used to be in terms of a variable x and y. And what the change in variable, the Jacobian, allows you to do by this formula here is to convert it into u and v. So I want you to imagine you've got a region in 2D space called, say, D. You've got a function like x squared plus e to the x plus y, whatever, and you're going to integrate it with respect to x and y. What the change in variable formula is indicating here is that you can find a different double integral that's got the same value as that. But instead of the function being in terms of x and y, we're going to convert it to u and v's. We're going to then multiply by the Jacobian and integrate with respect to the new variable u and v. That does mean, however, that the limits of integration that used to be using x's and y's have to also get transformed to using u's and v's, and that isn't always as obvious or as clear as you think it should be. So first couple of questions are going to be Jacobians, just to get a little bit more practice, a little overlap. I'm going to do a 2x2, and then I'm going to do, I think I've done the 3x3, but if not, I'm still going to do another one. So let's do x is equal to u e to the v, and let's suppose y is v e to the u. I'm putting a kind of asymmetric spin on this. Then if you want to find the Jacobian of xy with respect to u and v, you create a 2x2 matrix and you get its discriminant. And it's x with respect to u and then with respect to v. And then on the second row, the partial derivative of y with respect to u, get the order right, and then y with respect to v. So that's going to equal, if you differentiate this with respect to u, you get e to the v. And if you do it with respect to v, you get the same guy you started with. If you do this guy with respect to u, you get the guy you started with. And this guy with respect to v, you get that. And then we have a 2x2 matrix, and its determinant is major diagonal take away minor diagonal. So that's going to be e to the v times e to the u, take away u e to the v, v e to the u. Okay. And these two guys combine and get you u plus v. These two guys multiply together and get you that. And for style points, you would pull out your guy. And that's your Jacobian. And you get what, 3 or 4 questions where they just ask you to calculate the Jacobian, and that's it. Are we comfortable with the process? Right. Here's your formula. Find the bits. Right. The discriminant is major diagonal. That's multiply these. Subtract minor diagonal. Multiply these. Tidy up. For completeness sake, even although we're not going to do a change of variable with 3, we should, see what it looks like when you try. So let's suppose that we have 3 variables. Let's say x, y, and z. And x is going to be u plus v plus w. Y is going to be UV, and Z is going to be VW, right? So that's going to be my essentially 3 U subs in 1, right? Now you want to find the Jacobian of XYZ with respect to U, V, W. Now, this doesn't make sense unless 3 goes with 3, right? You can't do a 3 with 2, because what you'd end up with is a matrix that had more rows and columns, and discriminants don't exist for those shapes. So it has to be a 3 by 3, which, if you think about it, a 3-dimensional space turning into a different 3-dimensional space, you kind of have to have that, right? You can't take 3 dimensions and crunch it into 2. You'd probably be breaking some laws of physics if you try to do that. Well, the formula is going to be very messy. You take X and you do it with respect to U, then V, and then W. And then you take Y and you differentiate it with respect to U, partial derivative, with respect to V, and with W. And then you do Z, and you do it one more time. So you do it with respect to U, with respect to V, with respect to W. Now that's going to mean when I'm finished that I'm going to have a 3 by 3 matrix. And the discriminant of that's a little bit trickier, but we'll worry about that when we get to it. Right, take the top guy. With respect to U, with respect to V, and with respect to W, you get a nice easy answer. 1, 1, and 1. Right, the second guy. With respect to U, that gets you V. Differentiate it with respect to V, that gets you U. Differentiate with respect to W, and you get nothing. Then you go to the third one. With respect to U, you get nothing. With respect to V, you get W. And with respect to W, you get V. Are you comfortable about this, the 9 terms? Right. Now, the rule for doing a 3 by 3 matrix is a little bit trickier. It's basically, you use the top row. So you're going to have 1 times some stuff, take away 1 times some stuff, plus 1 times some stuff. So if that's 1, 8, 2, it'd be 1, 8, and 2. Right. Now, what's the stuff? Right. If you want to do the first one, cover up the rows and columns. When you do that, there's a little 2 by 2 matrix left. You go major, take away minor, UV, take away nothing. Right, you want the middle one now. V squared, take away nothing. You want the last one. VW, take away nothing. Right, so if you want to get the first guy, second guy, third guy, right, it's very visual. Right. And let's see what I got here. UV times 1 is just UV. Take away a V squared. Oh, add a VW. That would be the 3 by 3 discriminant. Remember I mentioned polar. Remember the extra R that you got, and I did that one on Thursday. That R is the Jacobian. If you go back and you look at the cylindrical coordinates that we did, and then after that, the spherical coordinates we did, see if you did those guys, do you know that extra rho squared, God, I can never remember what it is now, sine phi thing, right? That comes from the Jacobian, right? So that's where those weird bits that we just said, trust me, I'm a mathematician, that's where they came from.
Where did the +1 come from? Like 1 plus VW?
1 plus VW.
At the very end.
This one came from that guy.
The positive.
Right, the pattern is always plus this guy, minus this guy, plus this guy. So plus this guy, minus this guy, plus this guy.
Okay, that makes sense then. Thanks.
You'll never want to do a 4 by 4, but if you wanted to do a 4 by 4, plus, minus, and each one of them generates a 3x3 matrix, which you then do, you do the same process that we did here, and God, it takes you forever. So unless you're doing 252 linear algebra? Anybody done 250 linear algebra? I got one.
Linear algebra.
I did.
Right. When you did the 250, I'm pretty sure you done 3x3s.
Yeah, you do.
Yeah.
But did you ever even go near 4x4s for pretty obvious reasons why you probably did?
Yes, we did.
Never.
I did.
Oh,
Oh,
you did?
yeah.
Was it a pain in the butt?
Yes.
Right, Christian will tell you why we don't do 4x4s then, right? They're a pain in the butt, right? Actually, can't you just go to a computer and say, do it for me? Which is what you would do in reality.
Yeah, your calculator helps you out a lot with those.
Well, yeah, because you can do row echelon form and so on as well. Okay, so it's time for us to actually look at an application of using a change in variable, right? And see if I can pick an easy one to start the ball rolling, because no, that's okay, but I'd like a better one if I could. Oh God, that's horrible. I don't want to do that one first. 7, I can do that one. Right, let's do 7. In question 7, you're being asked to do a double integral of some region R, which happens to be an ellipse, and the ellipse is 30x squared 25 y squared equals 900. That's the ellipse. And we're being asked to use x equals 5u and y equals 6v as our change in variable, right? And the function that we're being asked to integrate is 9x squared dx dy. So according to this formula, I have to figure out what the range in these values look like, right? And why haven't you given me that answer? Oh, I want to make sure I've got the answer so I can keep track of it. Right, anyway, back to the question. Since there's a lot of pieces that all have to fit together, the first piece I'm going to find is the Jacobian in this question. Now, sometimes what's going to happen is that they don't make it obvious who these two guys are. That's why I picked this one, right? Because it might not be obvious what your U sub is going to be, right? What your change in variable is going to be. So if you had that, there'd be a step 0 up here, which would be create this, and then step after that would be Jacobian. So you differentiate x with respect to u and v, and you differentiate y with respect to u and v. And this guy, when you differentiate with u, gets you 5, and with v, you get nothing. This guy, you get nothing with u and 6 with v, and you get 30 major, take away 0, which is 30. Okay, didn't happen here, but it can happen. Suppose that answer was negative 30. What is the Jacobian equal to?
30.
30. So remember, the Jacobian should always be positive when this is a number, right? So if you do a Jacobian and you get a negative 42, you will just write down 42. Otherwise, your answer will be the same number, but numeric, the sign will be wrong, right? So those little vertical lines around this guy are also like an absolute value, right? They are making it positive. Now, when the expression has u cubes and v's in it, you can't really, you just have to assume it's positive, right? Because it's hard to tell, right? I mean, is u squared minus 2v positive or negative? Well, doesn't it depend, right? There's no way of telling. So it'll be cool about step 1, getting that guy. Now, taking this nice and slow. Step 2 would be to take your function, whatever it happens to be, convert it into the other variable. In this case, it's 9x squared. So that's going to be 9 5u squared, which is what? 9 times 25u squared, which is 4 gets you 100, 4 gets you 100, so 225u squared. Are you comfortable about the conversion of the function in terms of u? Any questions so far before I move on in the next phase? Silence is good. Now, I'm going to take the region R, which is basically this guy, right? And I need to convert this guy into limits of integration using u's and v's. So I'm going to start, I guess I should call that step 3, which is find the limits of integration for u and v. So I'll start off with the region that they gave me, which is essentially that guy. I'm going to replace the x with 5u, and I'm going to replace the y with 6v. And so in terms of x and y, this region R is going to turn into this region S. Are you comfortable with why that works, right? The x's and y's are now going to be converted into a relationship using u's and v's. And 36 times 25 gets me 900 u squared plus 900 v squared equals 900, which actually just becomes that guy. So the original region R was an ellipse. Under this change in variable, doesn't it just become a unit circle? So far, so good. Now, as if life wasn't bad enough, we are going to have to use another change in variable, but we can get away with this one because don't you recognize a circle, and circles should make you think polar, right? It's a 2D polar. So I'm going to call u equals r cos theta. I'm going to call y equals r sin theta. And if I did, but I don't need to, couldn't I go through all this Jacobian process and prove to you that the Jacobian was r? But we know what that is because it's polar. So what do I have? I'm going to have r goes from 0 to 1. Since it's a whole circle, 0 to 2 pi. My integral then is now going to be the integral from theta equals 0 to theta equals 2 pi. My integral from r equals 0 to r equals 1. Right now, it's 225 u squared times r. Oh, where's my Jacobian? Putting my Jacobian first. 30 times r dr d theta. That guy there is him. That's him. That's him. And these 3 guys are him. I almost forgot that 30 guy. Now, I've still got a fair amount of work, but every step gets me closer to what I need. Can't I take the 30 and the 225, right? What do you think I'm going to rewrite u squared as? Because we've essentially done a change in variable twice. So what's u squared going to become?
Wouldn't
Any
u
takers?
squared be r squared cosine squared of theta?
That guy and that guy I've brought out as a big ugly function. Okay. The original integral, where's that original integral? Right. The original integral was the double integral of 9x squared over an ellipse. Now, if you try to do that with week 3's work, I think it would be week 3 anyway, week 2, 3, wouldn't that be horrendous to try and do as a limit of, I mean, just that, and you're going to have some weird, ugly square roots all over the place, and you're probably going to end up with integrals that are not going to work well. So we're told to use this changing variable. We got a Jacobian, which is basically 30. We converted the function into u's, and we converted the ellipse into something in terms of u and v, and it ended up being a circle. But a circle's a lot easier to deal with than an ellipse ever would be, right? And that circle has a radius of 1, so that generated a new changing variable, r and theta. Put in the r and thetas. There's our f of xy converted into u's and v's. There's my Jacobian, and there's my du dv converted into polar. Pull out all the numbers, and we're at this point here. I'm pretty close to finishing here. Is this guy variable separable?
Real quick, wouldn't the r squared cosine squared theta be r cubed?
Correct. Is this variable separable? Yep. Won't integrating r cubed be easy? And won't integrating cos squared be a half 1 plus the cosine of 2 theta because you've done it 10 times now? And off you go. And according to what I have here, you get 3375 over 2 pi, which is basically that guy divided by 4, which I could believe. Right, you think that one was easy? You ain't seen nothing yet. If you think this one is hard, you definitely haven't seen anything yet. So I'm going to go back and I'm going to pick one of the early ones that I missed. And that's question 5. Question 6 is very like it, so I'll just do 5. You're being asked to find a double integral over a region R. It's x take away 10y. Well, they're calling it dA, but I'm going to call it dx dy because that's who dA is. And we're going to do x equals 9u plus v. And we're going to do y equals u plus 9v. And the region R is a triangle that you get by joining the origin to 9, 1 to 1, 9. Okay, so I got this guy, so that's at least something. So let me get the Jacobian piece of the puzzle out of the way. With respect to u and v, with respect to u and v. If you do this with u, you get 9. If you do it with v, you get 1. Do this with u, you get 1. Do this with v, you get 9. 81 take away 1 gets me 80. Oh, that's not bad. Nice number, it's positive. The x take away 10y bit, which is essentially my f of xy fella, he's going to be 9u odd v, take away 10 lots of u odd 9v. So it's going to be 9u odd v, take away 10u, take away 90v. And that's going to be negative 1u, negative yikes, negative 81v. Okay. That's that guy done. So far, so good. Right, I'm basically finding the Jacobian, turning this guy here into u's and v's, not very pretty. Now we're going to work on what does this look like in terms of limits of integration for u and v. So pretty visual, so I'm going to draw a pretty basic sketch of it. And I'm going to say, okay, you start at the origin. Okay, imagine that's 9, 1. There you go. All the way to here. And then you go 1, 9, pretend that's 1, 9. You go all the way up here. And then you go all the way over here. And that's region R, right? So far, so good. Now, how can we figure out what these guys are going to be in terms of u and v? Well, I'm going to call this guy A because I want to, this guy B, and this guy C. So let's find AB. Would you agree this is a straight line passing through the origin? So this side is going to be a straight line, and this straight line is going to have the equation y equals 1/9 x. Are we good? Now that's what it looks like in x's and y's. I want to know what that looks like in terms of u's and v's, right? So y is u plus 9v, and x is 9u add v. And I don't know why I'm red, so I'm back to my usual now. So that one line ends up being this guy. And these cancel out, and God in Himmel, that's 9981 take away 89th v. Actually, doesn't that just transfer to v equals 0? Is that kind of interesting that you got a number out of a line? Now, I'm now going to do AC, because I think that might be interesting. And AC is also a straight line, but the difference here is that y would be 9 times x. So you're comfortable with slope and rise and run, right? AC is that guy. Now, according to what we have, u plus 9v is 9 lots of 9u plus v. And so u plus 9v is 81u plus 9v. And that gets me u equals 0. You still with me? So I'm going to describe this region that's in x's and y's right now, and I'm going to describe it in terms of u and v. And it looked like 2 of the straight lines that ended up being horizontal and vertical lines, which I will draw in a minute, but not yet, because I have one last line, which is the line BC. And that basically that is the line joining 9-1 to 1-9, agreed? That one's going to be the messy one. So if I want to do the slope, it's 9 take away 1 over 1 take away 9, which is 8 over -8. So the slope is -1. And if I do y take away y1 equals m x take away x1, I will get 1, I'll pick this guy as x1, y1. Take away 1 is -1, x take away 9. As far as you can tell, am I good? Now, that is the equation of that line using x's and y's. Don't I now have to find out what the equation of that line is going to look like in terms of u and v? And every other time, didn't I replace u and v by, well, y gets replaced by this fella, right? And x gets replaced by this guy. So y becomes u plus 9v, and negative x becomes negative 9u plus v as 10. So u plus 9v is negative 9u, negative v plus 10. Oh, add it to both sides, you get 10u. Add it to both sides, you get 10v equals 10. Oh, that's not too bad. U plus v equals 1. And I think that comes out quite nicely as v equals 1 minus u. I'm thinking of u and v alphabetically like x and y. So this triangle, right, in xy space is now going to be turned into uv space. And what do we get? Well, we got u equals 0, which is basically that vertical line there. Right? And v equals 0, which is that horizontal line here. And then v equals 1 minus u is basically this guy. Isn't that a much nicer triangle to deal with? Right? So this is our new region. This is the guy that we would call S. Now, its limits of integration, you do exactly what you would do in XY space when you do a little vertical guy. And I would say U goes from 0 to 1. And won't v go from 0 to 1 minus u? And that is the limits of integration. So from this triangle, we found out what the three sides were in u and v. We now have a new region in uv space, which gives me these limits of integration. So when I put the whole package together, this guy, it's going to be from u equals 0 to u equals 1, from v equals 0 to v equals 1 minus u. So far, so good. This function here became negative u take away 81v. The Jacobian comes next, 80, and then dv du. I think I won't take it much further. I'll probably pull out the 80. Would you agree that that is doable? It's just a normal double integral. Okay, it's got u's and v's, but that's it. Now I'm trying to see if I can, oh, there we are. If you were wanting to do this without doing a change in variable, right? If you try and go vertical, right? Do you see the problem? Don't the equation of the bottom and top change as you slide from left to right? Well, what about going horizontal? Don't you have the same problem after you pass B? So do you see you won't be able to do the vertical, the type 1, or horizontal type 2. So you wouldn't be able to generate limits of integration of that triangle because of its orientation, right? So you're stuck. In the one that we did before that, if you try and find the limits of integration of an ellipse, the math is kind of doable in the sense you could set up a limit of integration with x's and y's, but you would be left with some really ugly, you know, y equals whatever, 1 minus x squared over 256 to deal with. And I think you'd probably end up having such a horrible integral it might not even be doable. So sometimes you do a change in variable because the integration is just impossible. Sometimes you do it because you cannot find, in terms of x and y at least, limits of integration that would work. So this triangle works. Can I also do it the other way? So if you're wondering why I went this road, I think u is like x and v is like y. That's just the way my brain works. It could have changed. Same answer. Was I right about how scary it was? Lots of places to go wrong. Question 6 is just like that one, so I'm not going to attempt that. We have done a 7, so let's get by that. Whoa. I'm looking at the time. Okay, jump in head first. 8. This is the original question. The region R is described as another one of those ellipses. Except I bet you if you sketch this ellipse, it would be an ellipse orientated at an angle, which is even worse looking than it would have been before. Now, if you tried to do that in terms of x and y, would you agree that you couldn't even set it up? You might be able to say x is 1 to 9, but forget about trying to figure out what the bottom is, because won't you have to rewrite this as a y equals, and I'm not even sure it's doable. So sometimes it's impossible even to do the question, even if you tried to. So we now have to work on who the changing variable is. And I'm making sure I've written this right, because that's why I went, oh no. No. I did go and do it wrong. We try that again. I blame them. It's hard to read the guy that they want you to do. So it's the square root of 3/5 u. Well, it's not. X, obviously bang would stop as well. We got this guy. Take away that guy. There we go. And we've got this guy. Add that guy. Not even a pretty example of the substitution, right? But they're telling me, right? So thankfully they did that, because I would not want to create what that looked like. Now, if I do a Jacobian of this one, I'll save some time. If you do this with u, you get that guy. If you do it with v, you get that guy. If you do this with u, you get that guy. If you do this with v, you get that guy. If you do major take away minor, I'll take their word for it. It's 6 over the square root of 115, which that gets you 3, and that gets you take away a negative, that gets you another 3, so that's where the 6. And those two get you 115. Okay, that makes sense. And it's positive, so I'm good. Now, the next piece of the puzzle is we're going to figure out what this function looks like in terms of u and v. So it's going to be 7 times And I'm definitely going to cheat here. Not just because of time, because it's so ugly, I would screw it up. That guy, take away 9 times. That guy times plus 7 times actually that's the minus and that's the plus, not really matters because it's the same product. And this guy here is that guy. And you're going to trust me, but what do you get? You get u squared plus v squared. Oh, by the way, this thing is equal to 3. When you do it, you get that guy. So horrible ellipse turned into a unit circle again. So can you trust me, if you multiply that all out, you just end up with a u squared plus a v squared. And I'm assuming there's a 2 here that cancels out with that and leaves me with a 1. Kind of miraculous, but it worked. Now, I know what that looks like in UV space. So can't I just do r cos theta, r sin theta? In which case, the r goes from 0 to 1 again, and the theta goes from 0 to 2 pi. So I got my Jacobian here. I've got my limits of integration in terms of r and theta, and this horrible expression here happens to be the same thing as basically that guy. So this horrible expression is equal to. No, okay. I'm trying to check from what they've got here. Anyway, I should start it. Oh, I've got this guy here. Well, I'll put it back in. If you find out what does that look like in terms of U and V, can you trust me? They tell me it's that. I'll take their word for it. So I've got all the pieces then. I have my double integral. Theta is 0 to 2 pi. R equals 0 to R equals 1. The function is this fella. The Jacobian was this fella. And an r dr d theta. Oh, wait a minute. What does u squared plus v squared look like? Well, if you do my polar, doesn't that end up being 1? So you get 3. So you've got this guy to 2 pi. Oh, this is going to come out nice. 3 times 1 is 3. So the original integral should be under here. Huh? The original integral, which was this guy here, turns into basically 18 over the square root of 115 of an integral from 0 to 2 pi, an integral from r equals 0 to 1 of just r. And that's pretty easy to do. definitely made a mess of that one. I hope you could keep track of it all. Mostly because the algebra was ridiculous. You know, normally they make these come out as 2s and 3s, don't they? You know, they make nice substitutions that come out pretty. But evidently not this time. They had to pick something really horrible. Variable separable, 2 pi, half r squared, right? Half r squared gets you half, 2 pi gets you pi. So may as well take it to the end. That would be the answer.